All right. So welcome, everyone. Thanks for joining me today. I'm Colin MacNaughton. I head up engineering at Neve Research. We're the creators of the X platform, a platform that's designed around making authoring in-memory applications really, really easy without compromising on performance. So me and my peers, we're all very passionate about high-performance computing and sort of pushing architectures that truly scale and make developers' lives easier. So we're talking about streaming today, specifically exactly once stateful streaming. And I wanted to sort of start by talking about why we care about it, but it's interesting. Since I spoke last at the In-Memory Computing conference in San Francisco in November, I'm seeing a lot more vendors here talking about stream processing that's stateful and on big data. So it seems like sort of people are beginning to realize the power of sort of streaming. So I kind of found it interesting today to hear sort of the focus on streaming. So for me, I think streaming is getting to be popular because we're moving towards more loosely coupled architectures. So it's very helpful for us as developers if we can move away from monolithic architectures to smaller sort of microservice multi-agent architectures. For our developers, that makes life easier because we're working on a smaller, more manageable piece of code where I can sort of fail fast or succeed quickly. So I can achieve sort of more predictable development timelines if I'm working on a smaller piece of the problem, and it makes my organization overall more agile. But we're living in a world of big data right now, so if I'm going to break my application down into smaller pieces, I've got a lot of data to move between these applications. So the better that I can stream that data, and if I can do that at low latency and high throughput, the better my overall application is going to perform. And so why exactly once? You can do streaming, and streaming's not so hard to do in sort of a guaranteed fashion, but you have to worry about duplicates, and you have to worry about message loss. If you as a developer can count on exactly once delivery and processing, it makes developers' lives easier and our applications overall more robust. So that's why we're still talking about streaming. So today I'm going to talk about what makes streaming hard and sort of talk about some of the challenges of really doing high performance, low latency streaming, what's sort of difficult about it, and why doing it at exactly once in particular is hard. How to do it in a reliable fashion, why that's hard. And hopefully you'll find that useful when you're sort of listening to other presentations here over the next day or so when sort of thinking about how solutions are architected. And I'll tell you how we handled streaming in the X platform leveraging in-memory techniques and give you a sense of why sort of in-memory computing is really important when it comes to doing high throughput streaming. And then we'll look at a IoT use case just to see sort of what in-memory solutions can kind of do. So streaming applications, what do? They work like any other sort of application. We're going to take some inputs, do some computing. That will generally be stateful, meaning that we're going to update state. We're going to look at a bunch of state or data to do our processing, and we're going to emit some outputs. So no big magic here in streaming. The only sort of thing that we're focusing on today is trying to do that with a fire hose of events coming at us. You know, how is that sort of hard? So non-functional things that we want to worry about when we're thinking about streaming applications, non-functional being things that have nothing to do with the business logic that we're writing as developers. Of course, we want it to be fast. That's sort of implied almost to me in streaming, so we're looking at getting into the tens of thousands of transactions per second or hundreds of thousands, millions of transactions per second. We're talking specifically about stateful streaming today, so streaming where I'm looking at large data sets and data sets that I'm concurrently updating while I'm trying to read that data. We want our applications to be reliable. We're sort of talking about microservices architectures here, so this is sort of mission critical streaming we're doing in the front end. We're talking to customers. Can't have any data loss when working in the front end or back end or really anywhere. And these applications need to be highly available. So if this is fronting my business, can't accept any downtime. So We need high availability, reliability, and of course we need to scale. As our business is successful, we expect more volume and demand, so we want to be able to scale wide to grow with our business needs. Streaming in and of itself is also sort of volatile in nature. I need to be able to respond to spikes. So I need to be able to scale out to meet any sort of new volume, or I'm going to start pushing back on systems upstream. And then, sort of like any sort of application platform and environment, got to be manageable, got to be very easy to deploy these applications and monitor and manage them. So all of those non-functional aspects we want to achieve, and we want to do so in a fashion that's really easy and productive from a developer standpoint. We want developers focusing on the domain problem at hand. So how can we sort of develop streaming platforms that don't make developers kind of think about all these non-functional aspects? So talking about performance, the way I like to think about streaming is in terms of microseconds. When you're streaming, what you can't do is block. That's sort of the opposite of streaming. So I like to think about what does any sort of thing that I'm doing in my application that might take, say, a millisecond do to my ability to stream. And of course, there's 1,000 milliseconds in a second. So if I do something that takes a millisecond, my streaming rate is now capped at 1,000 messages per second, or events per second. That's really important because if I'm processing an ordered stream, where a subsequent event might depend on the processing of an event that I processed in the past, I can't really just make those streams go parallel. So we need sort of really robust infrastructure and a streaming solution that operates really down in the microseconds if I want to scale up and be able to process massive streams that are in the tens or hundreds of thousands of transactions per second. And we're here at the In-Memory Computing Summit, so the spoiler is that you can't really achieve that without using an in-memory technology. So I like to show this table to sort of highlight the cost of what going to disk costs you when it comes to streaming. One of the things we're going to do if we're doing stateful streaming is we're going to be updating state. As you can see at the bottom of the table here, any sort of operation that's going to disk is sort of out of the question if we want to do high throughput streaming. So we're definitely up in sort of doing either network level writes or writes to main memory. And even a network level read, this table's a little old, but you're sort of in the 40 microseconds, 100 microseconds level to make a synchronous write operation over the network. So what can we do in sort of our streaming architectures to stay squarely in our own memory space without blocking? And how can we do that more specifically in a reliable fashion where we're not going to lose data or compromise on high availability? So let's take a look at some of the challenges associated with exactly one streaming and just sort of some of the places where we might end up blocking our stream processing. Firstly, if we're going to do exactly once streaming, exactly once eventing, that means that in terms of any message processing I'm doing, I'm going to have to use an acknowledged protocol. So even if I'm doing HTTP, if I'm doing more likely something like Kafka or Solace or JMS, if I don't want to lose a message, I'm going to be acknowledging that message back to the sender, so if I fail, I can get that message redelivered. Same thing with outbound messages. I can't forget about the message that I'm sending to as an output of processing until I get an acknowledgement back from the person downstream. So I've got this sort of potentially synchronous operation that I have to do both from the receiving end and outbound end that's going out over the network. And if we remember our last slide, that's going to potentially give us problems. The more typical one that we think about is sort of the data access piece. So if I need to read data from out of process and I have to fetch it over the network, again, I'm sort of beginning to do a synchronous operation that's going to impede my ability to stream. And writing is even more difficult. I have to sort of write out to the process and potentially down to a disk somewhere, which again is going to interrupt my ability to stream. So let's just take a look at some of the evolutions of traditional application architectures and their suitability for being able to stream. So the traditional, 2000s architecture of a relational database and an application that achieves scale by launching additional instances in a processing tier. This obviously doesn't scale to a point, but the main point that prevents you from streaming is that you have all of these applications trying to write to a single data source. And if they're all doing updates, they're going to be doing so under some sort of level of transaction isolation. If I'm trying to achieve high availability with these instances, I need to make sure that if the instance on the left crashes, another instance can go and pick up with a consistent state of the database. So you can imagine as I scale this wider, I just get more transaction contention on the database, and I'm sort of operating in hundreds of messages per second rather than where we want to be. It's also difficult in an architecture like this to do sort of ordered stream processing. If I'm sort of sticking stuff behind a load balancer, how do I sort of manage the ordering of the requests coming in? That's one of the reasons why you end up doing sort of really high isolation levels in the database. So going to a database, especially one backed by disk, is not going to do it for you for streaming. So the next sort of evolution that we sort of evolved to in data management was to launch that data into memory. So at least now when I'm going to make a state update over the network, it only has to go to memory in at least 2 nodes in the data fabric. So conceivably, I get a response back indicating that I've stored my state changes a little bit faster. But ultimately, it's no different than a database model where all of the application tier needs to do some sort of locking or transaction level concurrency to hold, to keep the state in a consistent view. So what do we do to get around the sort of storage bottleneck? The best way that we've seen for people to do it is to start thinking about partitioning your state and move towards a more microservices model and a microservices model on sort of steroids. So if my main bottleneck in the previous examples was contention on data updates, if I can partition my application out across separate private data stores, this is the microservices model of having private state for any service, where that state can only be updated over a messaging fabric, then I've suddenly eliminated all of the contention that I have on state updates, and I can truly scale in parallel. So this is the first sort of architecture that we've looked at today that will actually scale as far and wide as you can go. I can launch more instances. I'm not going to have contention on my state. There are still a couple of challenges in this architecture that prevent us from actually being able to stream. So one piece is that the data that we're using for our processing is still outside of our process. We have to go and fetch it from a remote process. And if we go back to that table, that means a lookup over the network. I can mitigate that somewhat by using some sort of caching technology in my application tier. Then I don't have as much latency when I'm reading. Maybe my data is going to be there. But when it comes to updates, I still have to write it to the storage medium because if I fail, I need some other instance of my application to take over. So we're still looking at a network write to achieve a lot reliability. And then the other sort of complexity that we have to deal with here is how do we manage our routing if we've now partitioned our state. If we imagine this as an application that's managing customer data, right? I might be able to partition my state saying all customers with last name A are in the left with B are in the middle. But how do I map my inbound requests to the right instance? So I have to think about some sort of routing that I, as a developer, have to solve to make sure my requests go to the place where the data is actually being stored. So I've got a little bit of complexity there. But the subtle one that people don't really think about is if I want to do exactly once processing, how do I make sure that my messaging stream is in sync with my data stream? So I don't want to process a request twice if I fail and have my data stored from a prior processing of that request already in the storage fabric, because by the time I fail over to a different instance, I might have a different result. So that sort of leads you into a place where you're looking at doing some sort of distributed transaction coordination between your messaging layer and your storage layer. And if you're doing a distributed transaction and there's a third-party controller, you're likely also looking at some sort of network call-out to do that. So these sort of synchronous operations make it difficult for us to stream. So just to summarize this architecture, definitely a lot better than the old RDBMS, but you're sort of operating in the thousands of transactions per second, and you're looking at multi-millisecond calls when end-to-end latency your response time. Primarily, that's because of your data really living primarily out of your process and having to deal with the synchronous protocols associated with keeping your message stream in sync with your data stream. From an application developer's point of view, that also doesn't really meet my goal of wanting it to be easy for developers. You still have to think in your application about how do I, managing the transactions with the database, doing synchronization, and making sure that I'm tracking enough state so that if I fail over to another instance, I'm not going to reprocess requests. So how did we solve this in the X platform? First, let me just tell you a bit about what the X platform does, and then we can look at how we tackle streaming. So the X platform, like I said at the top of the hour, is really a platform designed around trying to make it easy to write these stateful stream processors that are multi-agent in nature. So we do this by giving you a couple of facilities to work with. The first one is giving you the ability to work with RAM as if it were durable. And we do that, we'll see in a later slide, by replicating peer-to-peer to a backup instance. So we give you the facilities to model your state. We'll generate plain old Java objects for you to work with, maps, collections, objects, whatever you can think of in Java. Plain old Java objects, which during the course of your request processing, you can mutate, change fields, read them. They're all sitting there in the process with you, like right there in RAM. So no data access latency that you have to worry about. The other sort of key thing that the X platform does is we're a message-oriented platform. So we have a messaging abstraction layer which handles the messaging for you. So just like we model your state as plain old Java objects, we model messages as plain old Java objects. And the abstraction layer that we put on your messaging gives you sort of simple primitives to subscribe to messages and send messages. So we can plug into any sort of messaging provider out there, Kafka, Solace, 29West, JMS, whatever. As long as it can do guaranteed delivery, we can convert that to exactly once delivery. So from a developer standpoint, the programming model is really one in which you expose event handlers to the platform with a signature that says, I'm interested in this message. The platform takes care of making sure that you subscribe to get those messages. In your handler, any object that you touch or change, we're going to ensure that the changes you make to that object or set of objects is persistent across failures. And any message you send will get to any recipient in a once and only once fashion. And that whole process, which we can only do because we're managing your message and state, anything you do in a handler is exactly once. So because we think about sort of streaming at low latency and high performance applications, we've also created our platform to be zero garbage. So we're allowed in sort of Java to be able to do really sort of continuous streaming without any sort of garbage collection pauses, which is another sort of blocking operation that would impede our ability to stream. So how can we hold application state in RAM and still maintain reliability and high availability? If we're holding all of your state and data in memory, if my process crashes, I obviously can't lose that state. So what we've done in X is created a messaging flow in which we use hot backup instances, one or more backup instances of your application. When you launch one of your applications, it will discover any backup instances and form a primary backup relationship with one or more instances. When a message comes in, because you've exposed your event handlers to us by type, we know where to route the message. And because we generated those state objects that you're working with, we know what fields you're touching. So a request will come in. We'll be able to dispatch it to your application, know what changes you made, and because you're sending outbound messages through us, we can also control when those messages are sent outbound. So when your handler returns, effectively what happens is any state object you've touched, we will replicate to backup instances, and that gives you protection against your primary failing. What's a little bit subtle about what we do is that we don't deliver any outbound messages until we get an acknowledgement from the backup. So our ability to do a transaction, a scoped transaction related to your handler, is really predicated upon we don't say that that transaction is complete until we know it's been stabilized, its state changes have been stabilized in a backup instance. And from the outside's world point of view, that transaction has not been processed until you send outbound messages. The subtle thing about what we do is that because we don't send outbound messages until the backup acknowledges changes, we're a single-threaded architecture. So for any stream coming in being single-threaded, I can move on and start processing the next event in the stream before waiting for that acknowledgement. And that's really the key to being able to do streaming. We can't do anything that would block, and the way in which we do our replication means that there's nothing in the course of that processing that blocks at any point. So I've got a slide later that sort of looks a bit more at that architecture in depth if there are questions, but moving on, what does this mean for streaming performance? It means that for us on a single instance, we can do end-to-end latencies in microseconds, double-digit microseconds. We can do throughput on one instance at hundreds of thousands of transactions per second. And this is really important for us in certain use cases, like we're doing high-frequency trading on Wall Street, where it's not a very big stream of events coming in, but it really matters that you're first to market. And you're able to do that by having a processing flow that doesn't block at any point in the process. From a developer's point of view, this means that you have a programming model where your job as a developer is to model your messages and model your state using our state modeling and message modeling tools to expose to the platform, write your business logic, which is just plain old Java, whatever you want, or anything that runs on the JVM, expose those event handlers to the platform, and that's it. Underneath the covers, the platform converts your code into this highly available clustered architecture that we just talked about. So just looking a little bit more at the data flow in the platform, there are two other sort of features I want to call out. In this process of handling events, replicating, sending outbound messages, the sort of core transaction machinery and workflow in our platform, we also give you the ability to listen to state changes. We know every change you've made to any of your objects, and we can give you an asynchronous handler to listen to those changes and push into a back-end data warehouse. So very handy feature if you've got sort of an analytics database in the back end that you kind of want to be able to push out to asynchronously without impacting performance in the transaction plane. And so far, what we've talked about is sort of failure recovery and high availability sort of within a data center. If my primary instance goes down, I want to be able to seamlessly fail over to a backup and resume processing where I left off. We also will send that replication stream asynchronously out to remote data centers to ensure that even at a distant location, if there's a big disaster, your whole data center goes down, that your state is still captured in a transactionally consistent way remotely. So sum up for a developer, model messages, model state, write your code, a little bit of configuration. That's all you need. There's sort of no operational footprint that you have to kind of worry about. Just launch your application. So let's just take a look at what building a quick app would look like and what the performance characteristics would be with X. So we're going to do an IoT example. It's funny, I was just in here for William's talk, and he actually mentioned doing fleet tracking as well. So we built one of these on the X platform. Imagine sort of a FedEx or something where we want to track a global fleet of vehicles, make sure that they're obeying local speed limits, and more importantly, sort of staying within the routes that we expect them to, no packages falling off the truck. So an architecture like that, based on X, sort of a very microservices style architecture. We have administrators that are going to want to store the routes that they've configured for these vehicles. We modeled that in just one microservice we called the vehicle master. That's just basically a map that has a bunch of route objects. We also have a vehicle event gateway, which is accepting HTTP requests from vehicles and putting them onto the messaging fabric. In our lab, we ran with Solace as the messaging fabric, talking between all of these microservices. And then finally, the one I really want to focus on where the stream processing is happening is the vehicle event processor. And as those location updates come in from the fleet, that guy's job is solely just to absorb these streams, save the route that the truck has been following in memory, and generate alerts if it looks like that truck's outside the route. So this application is just written as a single class. I'm only looking at one method here, but and I'm sorry this is so small, but that's what it takes to program an X application, a method that takes a message and some state as its arguments. And what I mostly want to call out here is that this is just a bunch of Java code, plain old Java objects, where I'm not thinking about sort of any of the non-functional aspects of my application. I'm just sort of doing my business logic, which is what we're trying to make it easy for developers to do. So we'll look up the vehicle that corresponds to the message in a map, and there's a method we didn't include here, which is just doing calculations to see whether it's in bounds. And if it's out of bounds, we construct a route violation event, just a plain old Java object, and send it out. Yeah, don't need to go through that. And so this, on just one instance, will perform completely reliable, highly available. So one instance, when I say that, I mean a primary and a backup instance ready to take over at 130,000 transactions per second with an end-to-end response latency of 1 millisecond. And what's sort of key here is that 1 millisecond time is gated on how long it took the backup instance to say that it got the change in state to where the vehicle's location last was. If that were a synchronous call, we'd be going at 1,000 transactions per second. But because it's asynchronous and pipelined, and we can do it in batch, we're up at 130,000 transactions per second. So when I've given this demo before, and what's sort of nice is to actually run the demo and kill a process and sort of see that nothing gets lost in the process. But the main sort of takeaway here, very easy to turn just regular Java code into exactly once streaming code. So when it comes to X, if you can sort of, or any sort of streaming platform, if you can kind of find an architecture where you have no blocking and you don't have to worry about the transaction management between your state and your state update state stream and your messaging stream, it leaves you as a developer in a position where you can sort of focus on your domain logic. And that's all that we're trying to accomplish here at Neve. So an architecture like this, it doesn't require any sort of special hardware, just the servers we ran on were 2012 HP servers. So take a look at the code. It's up there in GitHub, and feel free to reach out. We're sort of here and listening. Went through that faster than I expected to, so hopefully there are some questions. Yes?
I actually have three questions.
Good, we've got plenty of time. Okay, so all good questions. The first question was, how do we handle ordering when we're dealing with asynchronous message delivery? Is that correct? So we can honor any ordering guarantee for the messaging fabric upon which you're plugging into the platform, whether it be our messaging product or Kafka or Solace, right? In our messaging abstraction layer, we model a channel as a sort of ordered conduit of delivery. So it's sort of our job to make sure that one channel remains ordered. So our business logic is single-threaded. So from that standpoint, I can track the order in which you sent events. And as long as they're on sort of the same ordered channel, then they'll be received by receivers in order. If they go out on separate channels, we don't really know who they're going to go to, and they could be processed in sort of any order. But for any particular receiver, it would be done in order in the way that you sent it. Depending on the messaging fabric you use, if you're using something like Solace, they'll honor total ordering across topics as well, and that can be useful. So there's a bit of flexibility in terms of what you choose to actually use for your messaging infrastructure there. Your second question was, what happens if a backup crashes while the primary is processing? So I didn't mention it before, but we are also saving all of your state changes to disk. So we have sequential transaction logs that can be used for like a cold start recovery. The sort of key thing is that because we're sort of writing that in one sequential stream, it's even friendly for magnetic medium. But we don't have to sync that data to disk because our primary backup mechanism is the backup instance. If this processor machine dies, I don't really care if that got synchronized to disk because I'm moving to this instance anyways. Now, if that instance goes away, we'll fall back to going synchronously to this disk. So it might mean that you have a reduction in throughput. But nothing stops you from launching 3 instances of your application, in which case you can survive one backup failing. The only difficulty with that is then your sort of hardware footprint and cost goes up. So it's sort of up to you to figure out what sort of degree of risk you're operating at. And then your third question was? Open source, yes. So the kernel of the platform, this atomic event processing, is closed source, but to our customers, we share the source with them, just not with our competitors. And then we have a whole monitoring framework I haven't talked about that allows you to suck all the data that's happening here. That's all open source. Our deployment tools are open source. Our microservices framework built on top of this is also open source. So we're a mix. It's just really that kernel piece that's closed source, but available to you as a customer anyways. Any other questions? Okay. Well, I guess everyone gets out early. Thank you. All right. So welcome, everyone. Thanks for joining me today. I'm Colin MacNaughton. I head up engineering at Neve Research. We're the creators of the X platform, a platform that's designed around making authoring in-memory applications really, really easy without compromising on performance. So me and my peers, we're all very passionate about high-performance computing and sort of pushing architectures that truly scale and make developers' lives easier. So we're talking about streaming today, specifically exactly once stateful streaming. And I wanted to sort of start by talking about why we care about it, but it's interesting. Since I spoke last at the In-Memory Computing conference in San Francisco,